Hello, today's topic is partial fraction decomposition. Okay, so we're in the section where we're learning various techniques of integration. I guess this isn't directly a technique of integration, rather it's a technique really in algebra that we're going to use to help us integrate certain functions, in particular fractions, as we'll see in just a second. Okay, so let's consider a simple integral. We've got the integral of 1 over x minus 2 minus 1 over x plus 2. And hopefully we recall our rules for log integration. If we integrate f prime of x over f of x, we'll get the natural log of f of x as our solution. And that applies in both cases here. The numerator is the derivative of the denominator. And so it's a very straightforward integral. It's the natural log of x minus 2 minus the log of x plus 2, and of course plus the constant of integration. Okay, so that's pretty straightforward. We'll also notice now, let's take these two fractions, and if we cross multiply and simplify a little bit, we'll get this. We'll get 4 over x squared minus 4. And so if these two terms equal this term, and the integral of those is here, then it must be true also that the integral of 4 over x squared minus 4 equals this. They're equal. The integral of one is this, and the integral of the other is this. Okay, so we know that the integral of 4 over x squared minus 4 is this term here with the natural logs. But how do we do that? How do we know that we can get backwards from this 4 over x squared minus 4 to the 1 over x minus 2 minus 1 over x plus 2? Okay, we're happy going in the one direction. How do we get back in the other direction? And that's what the partial fraction decomposition is going to help us do. Okay, we'll look at the key idea for today, and it's a bit dense, there's a lot going on here, so we'll just kind of work through it. First thing is that we have this rational function. We have a ratio of polynomials, and we're going to make this assumption that the numerator, the p of x here, has degree less than the degree of the denominator. Now, if that's not the case, we'll have to solve to fix that, and we'll see that right at the very end, but for the time being, we'll just kind of make this assumption that degree in the numerator is less than the degree in the denominator. Okay, and then let's look at this q of x. We'll let x minus a, we'll assume that x minus a divides q of x, and x minus a to the n is that largest power that does so. Then if we decompose this px over qx, then we should get this kind of term. We get a over x minus a, this linear term. We get another a2 over x minus a squared, and so on all the way up to an over x minus a to the n. So for example, if we just have x minus 2, and no higher power in qx, then all we'll get is a over x minus 2. If we had x minus 3 squared, we get an a over an x minus 3 and another a2 over x minus 3 squared. And so on up to that highest power. And we do that for each of the linear powers that divide qx. Secondly, we'll look at the quadratic terms. Okay, we'll let x squared plus bx plus c divide qx. And again, we'll take this highest power for that, if that's true, to be n. And then if we decompose it, well, it's just slightly different now. And for the numerator here, instead of having the a's, we'll have a bx plus c. Okay, and again, we'll have each one of those for each of the powers that we have. I should just note when we say quadratic terms here, we're going to assume irreducible quadratic terms. So if we had a x squared minus 4, we could actually break that apart, whereas if we have an x squared plus 4, we can't. So we're going to assume that those are irreducible. And so we do that for each of the quadratic terms we have in qx. And there's still more to do. Having found all that, we still have to find the coefficients, the a's, the b's, and the c's. Well, the first thing we do is we cross multiply to get rid of the denominators. We'll end up with the same denominator on each side. We'll see this in just a second. And having done that, well, there's actually a couple of ways of solving for the a's and b's and c's and so on. One way is to equate the powers of the x, so we get all the x squared together, all the x's together, all the constants together, and so on. And you'll get a system of linear equations that you can solve for the a's and b's and c's. And there is another way using the x's that we'll see that I prefer to use personally, that we'll see in just a moment. Okay, so as I say, there's a lot going on here. This is a pretty dense set of ideas. But as we work through examples, I think it'll be a little easier. And let's take a big example to start with. I'm not too concerned with the integration at this point. We're just going to try and do the decomposing. Okay, and we'll look here at this fraction. The q of x, remember, is the denominator here, where we have a linear term, with just an x minus 2. We have a repeated linear term, this is the x plus 2 squared. We have a quadratic term, the x squared plus 1. And we have a repeated quadratic term, the x squared plus 4 squared. Okay, so given what we saw previously, this is what we get when we decompose, and we'll just work through this. So the x minus 2 is a solo linear term, so we'll get the a over x minus 2. The x plus 2 squared is a repeated linear term, so we'll get a b over x plus 2 and a c over x plus 2 squared. And just notice this is slightly different. I use slightly different notation than the key idea we saw, whether it was A1 and A2 and A3. I'll just plow my way through the alphabet and see where we get to. Next we have the quadratic term, the x squared plus 1. Remember, instead of just a constant on the top there, we actually get the dx plus e in the numerator there. And then finally we get a repeated quadratic term. So again, we have the fx plus g over the x squared plus 4. And we have hx plus I over the x squared plus 4 squared, because it's repeated there. Okay, so, well, that's a bit of a doozy. Now, in theory, we could then start applying this to find a, b, c, d, e, f, g, h, and I. It doesn't sound like a great idea. You could do it, but it would take a long time and not be so easy. So we'll start with a simpler example where we want to do that. Okay, so this example, we're actually going to solve the integral. Okay, so we don't just have a term now, we have the integral of minus 3x plus 14 over x minus 4, x minus 3. Okay, so we'll see we have two linear terms here, they're not repeated, we just have two linear terms. And so if we drop the integral sign temporarily, we can say that the left hand side here, the fraction we had, is going to be equal to these two fractions, a over x minus 4 plus b over x minus 3. Okay, they were nice simple linear terms. And then we'll cross multiply here. This is a step, as we're going along, you can probably sort of go a little faster from this step to the next one. But if we just cross multiply on the right hand side, you can see we get ax minus 3 and bx minus 4. But by doing that, we have this x minus 4, x minus 3 denominator, which of course is the same as the denominator on the left hand side. We can therefore eliminate the denominator, and we're just left with this, the 3x, minus 3x plus 14, ax minus 3, bx minus 4. Okay, and as I noted previously, there is a way we can apply where we gather the like terms, gather all the powers of x on the right hand side and all the constants on the right hand side. There is another way we can do this, however. Right, this has to be true for all values of x. So we're going to pick a nice value of x to plug in. And when I say nice, it's not immediately apparent what that means. But as you get going, it'll be a little easier. But let's look here. This term, if we plug in x equals 3, the constant a disappears temporarily. So if we actually plug in x equals 3, we'll get minus 9 plus 14 on the left-hand side, and we'll get the b multiplied by negative 1 on the right-hand side, and so we get minus 5 equals negative b, so b equals negative 5. And having seen that, hopefully it's pretty obvious what the other easy value of x is. The easy value of x on the here would be x equals 4. And again, plug in x equals 4, we get, that should be negative 12. So we get negative 12 plus 14, which is 2, equals a times by 1, so a equals 2. Okay, so we've solved this. We found that the minus 3x plus 14 over x minus 4, x minus 3 is equal to 2 over x minus 4 minus 5 over x minus 3. We've done the partial fraction decomposition. Now we still have one more step, we still have to integrate, but now we know if these two things are equal, we can integrate on the right hand side here, which is much easier, as we just saw. If we wish to integrate that, in both cases they're just log integrals, so we get 2 natural log of x minus 4 minus 5 natural log of x minus 3, and the constant of integration. Not bad. Okay, let's make it slightly more complicated, not much. Again, just a quick note, the degree in the numerator here is 2, the degree in the denominator is 3, we have an x and an x squared, so we're still okay. Let's just keep recalling that rule about the highest power in the numerator and the denominator. And so if we wish to break this up, well now, because we have the quadratic term, the x minus 2 is still the same, we have a over x minus 2, But the x squared plus 7 will have a bx plus c in its numerator. Okay, that's the rule we saw. So I've skipped the intermediate step here, but I've just cross-multiplied and then cancelled out the denominator. And so we get the 5x squared minus 3x plus 19 is going to be equal to a multiplied by x squared plus 7. And then we get the bx plus c multiplied by x minus 2. And again, there's a couple of ways of solving for this. It's a little harder using our values of x, but I think we can still do it. And again, an obvious value of x this time would be x equals 2. And I'm not going to show all the working now, but if you plug in x equals 2 into everywhere here, you get, I think you get 33 equals 11a, and so a equals 3. There's not such an obvious next sort of out value for x, but if I plug in x equals 0, the b has disappeared, and the a we've already solved, and so you plug in and find it, and you'll find out that c equals 1. And then there's one more value of x we can plug in, and we can just take anything here, but again, I just want a nice easy number, so 1 seems like a pretty easy number. And because I already know a and c, I can quickly solve for b. And so I get that a equals 3, c equals 1, and b equals 2. Remember, we need to plug all those back in to this fraction here. And so sure enough, we get that this fraction on the left-hand side is equal to this broken apart fraction on the right-hand side, which we can hopefully now integrate. There's still a little bit of work to do. Okay, so if we integrate the left-hand side, we can integrate the right-hand side. The 3 over x minus 2 is a pretty straightforward integral, but it's a little hard on the right here. So actually, let's just break this fraction one more time. We still have the 3x over x minus 2, but we'll break apart the 2x over x squared plus 7 and the 1 over x squared plus 7. Hopefully you recognize this is again going to be some kind of natural log. This is also going to be a natural log. We still have that the numerator is a derivative of the denominator. This piece is going to be an arctan, which hopefully you recognize. You can look up in the tables. And so we get 3 natural log of x minus 2 plus log of x squared plus 7. And then we get 1 over root 7 and arctan r of x over root 7 plus c. And so that's how we do an irreducible quadratic. Now say we can keep repeated linear terms or repeated quadratic terms. And those aren't actually particularly hard as much as they are more. Okay, the more terms we get, the more complex it is, but it's not particularly more difficult. Okay, just one quick reminder. Suppose we want to do partial fraction decomposition here. Now we'll notice that the degree in the numerator is 3, whereas the degree in the denominator is 2, and we need that degree in the numerator to be less. And I should make that clear, it's less, not less than or equal to, it has to be less. Well, how do we do that? Well, we long divide. So we divide x squared minus 4 into the polynomial in the numerator, and it breaks down this way. We get x minus 2 plus x plus 1 over x squared minus 4. Okay, we still need to do our partial fractions on this piece, but now we can, because the degree in the numerator is less than the degree in the denominator. And of course, when we come to integrate, it doesn't matter that we have x minus 2 at the front here, because they're very easy to integrate. But we would just integrate the whole thing. So I say that's just a quick reminder of how we would apply it if the numerator has a greater degree than the denominator. And I think that's about it for partial fraction decomposition.